So this should be where we left off. Correct photoelectric effect, which we already talked about. So now we're going to talk about nuclear fission and nuclear fusion. So we'll start with nuclear fission. This is how we historically figured it out. So the definition of nuclear fission is to split an atom. So everything we've talked about up to this point is just stuff that happens in nature. Like naturally atoms are radioactive, they'll naturally fall apart. So we're going to start looking at nuclear fission, which is the process that humans use to split an atom. And then there's nuclear fusion, which we can also use to combine atoms. So here it gives you the definition. It says this is the result of either a nuclear reaction, that's what we do, or radioactive decay. So a little history for you. It says right here in 1938, the Germans Otto Hahn and Fritz Strassmann discovered that when the uranium-235 isotope was bombarded with neutrons, it absorbed them and split the lighter atoms and gave off energy. So that's significant because back in 1935, there was I think it was a Hungarian scientist by the name of Leo Szilard, who had left Europe. He was still pretty close. He was in England at the time. And he had this thought of how to make a unrestrained nuclear reaction. And he actually got it from a book. The book was by H.G. Wells, The World Set Free. So what I think is really interesting is that in this fictional book, they talked about things like how to harness the power of the atom. And in that book, they had a term called a nuclear bomb, an atomic bomb. And it's interesting because that word atomic bomb was actually created by a writer, completely for fictional purposes. But Leo Szilard had read that book, and he got him to thinking, like, could you do this in real life? And he thought, if you got enough of this stuff together, whatever it was, enough nuclei together, you could probably start a chain reaction that could cause an atomic bomb. He was so convinced that it would work, he wrote it down and had it patented in 1935. He patented the world's first atomic bomb. He patented it not because he wanted to make it, but because if you have a patent for it, nobody else can make it. That's how patents are supposed to work. But then in 1938, a few years later, these two guys had done this. And so the whole deal is, Leo Szilard basically knew in 1935 how to make an atomic bomb. But he wasn't entirely sure how to start, with what material. He figured it was going to be a neutron. You could fire a neutron to get this whole chain reaction started. But nobody had actually ever done that. What's interesting is a few years later, these two guys did it. Now, what's interesting is they weren't trying to make an atomic bomb or anything like that. They were just firing neutrons at stuff. It sounds weird, but that's totally something a scientist do. And it actually started way back with like Ernest Rutherford firing stuff, like that gold leaf experiment you heard about. So they were essentially just continuing this experiment onwards. And what's really interesting about it is that, it was 1938. What was happening in 1938 in Germany? It wasn't quite started yet, but yeah, pretty close. The important thing was the Nazis, who for some reason are back again. Nazis are bad, by the way. Just a little bit. It's important to note that, like Leo Szilard and some of these other people I'm talking about had left Germany or continental Europe because they were Jewish. So what's interesting about these two guys is they had split the uranium atom. They weren't trying to, they were just shooting stuff with neutrons to see what would happen. But when they got this data, they didn't understand what it was. So they sent it to their partners who had left Germany. They were living in Switzerland at the time because they were Jewish. They sent them their data and they were like, hey, what does this mean? And their lab partners realized what they had done. And they started telling everybody that these two guys had split the uranium atom. Now that's very important because, word got back to Leo Szilard of, hey, some people actually did the first step in your nuclear chain reaction. And he got a little concerned because, as I mentioned, the Nazis aren't good people. Once World War II got started, do you know some of the first countries they invaded? Austria. I'll show us a little far. Austria and Poland, and what is known as the Czech Republic now. You remember, last class when I showed you the video, he was like, oh, I went to the uranium mine, the mine where uranium was first discovered. Guess who controlled it? Yeah. So when you think, when Leo Szilard sat back and he looked at everything, he realized, like, okay, you just need enough of this material to make a bomb. And you just need something to fire this neutron. Well, guess who knows how to fire the neutron? These two guys in their German lab. Their lab just happens to be in Berlin. And it just so happens, like a year or so later, the Nazis now control the only uranium mine in Europe. So Leo Szilard got a little worried that the Nazis might try to build a nuclear bomb. And what's interesting is that, according to historical sources, people went to Hitler to tell him, hey, let's make a nuclear bomb. But apparently Hitler thought that was a crazy idea. So they didn't try to make one, but Leo Szilard did not know that. So Leo Szilard went to his good friend, and he asked his good friend to ask the President of the United States to start a nuclear weapons program, because we had to get it before the Nazis did. Leo Szilard's good friend was a little bit more famous than him. Y'all ever heard of Leo Szilard before I started saying his name? Now, his good friend who was a little bit more famous was named Albert Einstein. And Albert Einstein wrote a letter to the President of the United States because, for some reason, Albert Einstein had also left Germany and was living in America. And so when he wrote this letter to the President of the United States, let's just say the President paid a little bit more attention to it. So that's kind of a little bit of background, but you guys have to understand, like, the precipice of this program was essentially that Leo Szilard thought, he's like, this is how you build an atomic bomb. And he realizes that basically Nazi Germany has all of the ingredients. And literally no other country on earth was anywhere close to Germany's level of technology at the time. So, how do we use fission for peaceful purposes? Well, you can take some radioactive material. There's different types that you can use. But in general, when you hear about something like, Chernobyl or 3 Mile Island or Fukushima, like these are nuclear power plants. How do they work? Well, essentially what you have here is you have your reactor, and you have the nuclear material is here inside the reactor. And whatever it is, let's go for the sake of argument that it's like uranium 235, which is what you just saw on the last slide. You fire in a neutron, and the uranium atom here splits. And it doesn't just split, but it also splits and gives off other neutrons. You'll see that? Like, this is the process of nuclear fission, is the splitting of an atom. So they send in one neutron, it splits this atom into 2 other atomic nuclei, but also it gives off 2 or 3 other neutrons. And if those 2 or 3 other neutrons hit other, in this case uranium-235 nuclei, it can cause them to split and start this chain reaction that we've been talking about. So, let's say that that's what's happening here. It doesn't have to be uranium-235. But that's just for example. So here you have what are called control rods. Control rods are usually made of something very dense, you can think like lead. And so when the neutrons get fired in, if the control rods are up, passes the super hot pipe, boils and turns into steam. Steam rises, turns a turbine. The turbine turns a generator. We've already looked at how electricity and magnetism work. So you just turn the turbine, generates electricity. What's funny is that like a nuclear power plant is basically the same thing as like a wind turbine, except wind turbine is inside. So then as the wind passes through the turbine, they have a third piece of water coming from the outside, which this hot air will run by and then cool off and condense, and then go back inside. So you have one system of water here in the reactor, a second system turning the turbine, and then you have this third one, which is just used for cooling. And so you see these cooling towers here that are pretty typical of your nuclear power plant. But notice that like nuclear power plants tend to be on the side of like lakes or oceans because they need an external source of water. Now here's the deal. The only thing that comes out of this water here is heat. Like the water is warm. That is it. Now what happens here is eventually these nuclear materials are used up and they have to be taken out and they have to be sealed in barrels because they'll be radioactive for several million years. So there's a lot of pros here that they pretty much only emit water vapor and they're very, very efficient. But the con is that the radioactive fuel is still very radioactive for many centuries. All right, so do you have any questions of how this overall works? So that's how we use it to not work, so that's it. Here, there's a video you all can watch later. But this is a video of a nuclear reactor. The nuclear reactor is running. This is top-down shot of it running. And so what you're seeing here is you see these control rods down on the floor. This is a very small one. This is a test reactor. So here, you can see that. You'll notice that it looks blue. Anytime you look inside of a reactor, the water will look blue because of what they call here the shrink-off radiation. Essentially, the electrons that are given off in the water are traveling faster than the speed of light can travel in water, and so it always looks blue shifted. So there's a fun fact there. So that was nuclear fission, the splitting of nucleus. So I'll talk about nuclear fusion. So nuclear fusion happens when two or more light nuclei come together and fuse into something heavy. So here you have a picture of what we call the proton-proton chain for helium-4. And so notice you start with two hydrogen atoms or protons. They fuse together, and what comes out is an H2 nucleus. So here you can see that it gives off a positron, that's a little piece of antimatter I mentioned before, and a neutrino. Neutrinos pretty much don't interact with anything, and there's literally thousands of neutrinos passing through your body right now. It's fine. But then this H2 nuclei will combine with another proton and fuse, give off a gamma ray. This becomes H3, helium-3. And then that one will fuse with another helium-3, give off two protons, and give us the helium-4 nucleus. But in order for this to happen, you need really high temperature and really high pressure. Have we done nuclear fusion here on Earth? Yes. We do not have any nuclear fusion power plants because you need to get them really hot and under a lot of pressure for this to work. Because as I've said before, the hydrogen protons, or just protons, are positively charged. They don't want to be near each other. So you really got to force them together in order for that strong force to take over. We can do nuclear fusion, it's just not efficient enough for us to use it as a power source. Will we be able to use it as a power source? Maybe. The problem is that if you look back in the 1940s, 1950s, when we started doing all this, the estimate was, in just 20 years, we'll have nuclear fusion as a power plant. Now, nuclear fusion power plants would be really great. But is 100% sure it will ever work. Because essentially the only place we know that this happens very commonly is the sun. And not the surface of the sun, in the core of the sun. So, can we do it? Yes. Can we do it for an energy source? Maybe. There's some people that are absolutely certain that, oh yeah, just 10, 15 years from now, we'll be doing it. I'm like, if they were that certain, you'd be seeing a lot more research on it. But it always seems to be close. So, here, speaking of the sun, this is how the sun gets its energy. This is a picture of the sun, Earth for scale. That is to scale. There's a video there about where the sun gets its energy, but essentially, the sun is powered by nuclear fusion, but its actual power comes from E equals mc squared. Fun fact, if you look at the mass of a hydrogen atom, that 1.00794, and the mass of a helium, you could say it's 4.002, right? What's funny is that you go, okay, through that process I just showed you, essentially 4 protons become 2 protons and 2 neutrons, right? Well, if you take that 1.00794 and you multiply it by 4, you get 4, but not 4.0026. That 4.0026 is smaller, has less mass than just 4 protons. Now, it's not much less, but it's a little bit less. But if you take that little bit less and multiply it by the speed of light squared, that's how much energy you get. So every time you do nuclear fusion, you lose a little bit of mass. You convert mass to energy. In this process, the mass of the sun is reduced by 4 million tons per second. The sun is getting light by 4 million tons every second. Which is a lot, and it's hard to think about. And you're like, well, that can't be possible, but again, this is an actual picture of the sun next to an actual picture of the Earth. Instead. No. I'm just trying to show you how big this sun is. It can lose 4 million tons of mass per second for literally like 10 billion years, and it makes basically no difference in the size of the sun. Does that make sense? It's hard to grasp how big the sun is. So here, this talks about nuclear power, essentially cold fusion. There's a little video on it to help explain what's going on here. But essentially, what you're trying to do is do nuclear fusion at a temperature, well, less than the core of the sun. And we haven't been able to achieve that. All right, not everybody's favorite part, the atomic bomb. So, here's the deal. Whenever people talk about atomic bombs, first of all, I'll save it for the end so you pay attention. Going back to a little history lesson I gave you, once Einstein wrote his letter to the president became a little concerned. He formed a thing called the Uranium Committee. And the Uranium Committee basically sat down for a couple of years and they tried to figure out if what Einstein had said, being this friend Leo Szilard, is physically possible. If it was, how could we do these things? And they sat down and basically did a bunch of math for like 2 years to figure out, was this even possible? And if it was, how could we go about doing things? Because, for instance, Leo Szilard was like, hey, you could totally make an atomic bomb out of this uranium-235 stuff that they just studied in Germany. And they went, okay, where do you get uranium-235? And he said, well, it's out of the same pile you get uranium-238. So they went, okay, well, if they're in the same rock, theoretically you can separate them, right? But here's the problem. Uranium-235 and uranium-238 are exactly the same. Magnetically, they have the same charge, they have the same number of protons in the nucleus. The only difference between uranium-235 and uranium-238 is that 235 is missing 3 neutrons. So it's slightly lighter than uranium-238. So says right here that if you just dig up a rock of uranium, only 0.7% is uranium-235. 0.7% of the uranium you have is only the ones that you need to make a bomb. But here's the problem. You can't like chemically separate them. There's no chemical process that will prefer one over the other. They're the same chemical. There's no magnet that will pull one apart more than the other. There's no electrical process that will pull one apart from the other. They're the same. The only way to separate uranium-235 from uranium-238 is to deal with that slight mass difference, and it's very slight. And so what they did is, in America, we built this building. It's called the K-25 plant. You ever heard of it? No, you haven't. Here's the deal. Whenever people talk about the Manhattan Project, one of the things people don't understand is they're like, oh yeah, Manhattan Project, Los Alamos. Los Alamos was one of 3 labs in this country. Yes, one was in Los Alamos, New Mexico. That's eventually where everything went. But they also had a lab in Richland, Washington, and another one in Tennessee. This thing was built in Tennessee, in the middle of freaking nowhere. But you guys don't understand, this building was enormous. If there was roughly, let's keep numbers simple. Let's say they spent $4 million on the Manhattan Project. But let's assume it was a low number, like $4 million. Out of the $4 million they spent, almost $2.5 million would have been spent at this lab that no one's ever heard of. The single purpose of this K-25 plant was to separate uranium-238 from uranium-235. To put this in perspective, do you see these little trucks here? Those are 18-wheel trucks. Those are huge tractor trailers. This is an enormous building. So they built this, no one's ever heard of it, and now they've torn it down. It doesn't exist anymore. So when you're looking at this, they built this to enrich uranium. And make no mistake about it, some people thought, like a lot of the scientists that were working on the Manhattan Project thought, oh, we're going to build a bomb, we're going to detonate it, and we're not going to have to use it on people, and we're just going to have 1 or 2, just to have a threat. And that way, people will stop these wars. Until the scientists saw this building. If you saw this building, you realized one thing. The American government wasn't going to build 1 bomb or 2. They were going to build thousands. And guess what? We did. Here, this gives you a different set of reactions here, because it turns out that you can take uranium-238, hit it with a neutron, it becomes uranium-239. Then over time, it will naturally decay to neptunium and then plutonium. Plutonium is another product that we can use to make an atomic bomb. And the 2 types of bombs that we built in 1945, 2 were made out of uranium, 2 were made out of plutonium. So, when you're talking about an atomic bomb, you're talking about something that is using thermonuclear fission. Okay, that's an atomic bomb. That's what we made in 1945. Okay, that is using something like uranium or plutonium, shooting essentially a neutron or something heavier at it and causing it to split and detonate. To put things in perspective here, the bomb that was dropped on Hiroshima, that uranium bomb converted about 1 kilogram of mass to energy. If you take like E equals mc squared, there was 1 kilogram of mass, roughly, that was converted to energy. It was enough to destroy a city. Not every piece of radioactive material in that bomb went off. Some of it was still there. Some of it's still lingering around. There's different articles and videos here that you can explore these concepts further. But what's interesting is that's what an atomic bomb is, an A bomb. But we also have a thing called an H bomb, or a hydrogen bomb. A hydrogen bomb is a fusion bomb. Now what's the difference? Well, you guys ever started a car? When you go to start your car, you put your key in the ignition, you thing called a flywheel and cranks it. And it gets your engine started. Right? So your starter for your car is something, a little small thing to get your actual engine running. Does that make sense? For a hydrogen bomb, that's where we do nuclear fusion, fusing, hydrogen into helium. For an H-bomb to get started, we need a small reaction. It's true that we also need a small reaction to get an atomic bomb started. Now, to start an atomic bomb, they usually use something like plastic explosives, conventional explosives. They just explode one part and shoot it into the other part if they want. But in order to start a hydrogen reaction, in order to get the pressure and the temperature great enough for hydrogen to fuse, they have to use a small reaction. The starter that they use for a hydrogen bomb is an atomic bomb. To put that in perspective, they use a atomic explosion. They use an atomic bomb to start the hydrogen bomb. So hydrogen bombs are on a whole other level of destruction. Now, depending on what you do, hydrogen bombs really shouldn't have any waste material. But as I mentioned, with the atomic bombs, like the ones that were used in World War II, they don't all completely fizz. They don't all completely separate. And so it ends up spreading radioactive material everywhere. And so we call that nuclear fall. Now, when you're looking at this radioactive material, generally the smaller the bomb, the more radioactive material is left over. It's not able to fuse or fission quite as well. So here it says, depending on proximity to the blast and length of time exposed, these fission byproducts, the effects will vary. So here there's several news articles about acute radiation syndrome and radiation contamination versus exposure and what these terms mean. I highly recommend that y'all look these up so that y'all can hopefully understand some of what's going on here. So here, this is going to be the last slide that we cover today. This is really just a bunch of unit conversions. And I'm going to kind of explain what's going on here. So in the video we watched a couple classes ago, he talked about sieverts. So a sievert, so about 2 sieverts will kill you. So a sievert is 1,000 millisieverts, and that's what he was talking about, like a banana. It's like 1 millisievert. Does that make sense? But there's all of these other units for radiation that you can come across. There's rad, there's rem, there's gray, there's curie, becquerels, gigabecquerels, and so on. But what's interesting here is that some of them do different things. Like everything on the left side here is trying to use the radiation and say how much damage is it going to do. So that's your rad, your rem, your gray, your sieverts. Okay, sievert is just the metric equivalent. But on this side here we have curies and we have becquerels. And the whole deal is, when a Geiger counter beeps, that's just one beep. It just means that it got enough ionizing radiation. But here's the deal. Some radiation is more damaging than others. So what you can do here, it says, for gamma rays and X-rays, these beeps, you have to convert them to how much damage it's going to do to a person. So gamma rays and X-rays tend to be just a 1 on our scale, so it's just a 1-to-1. So you can say 1 rad is equal to 1 rem, which is equal to 10 millisieverts. So just 1 X-ray, 1 gamma ray, that's like getting 10 bananas. Does that make sense? But neutrons tend to be a little bit harder to stop, and they tend to go a little bit faster. And so they are somewhere between 5 and 20 rem, because we're trying to convert this radiation that you're getting into actual tissue damage. And then, so like a neutron is somewhere between 50 and 200 millisieverts, so somewhere between 50 and 200 bananas of radiation. But then alpha particles definitely equal 20. So 1 alpha is equivalent to eating 200 bananas. So you don't have to understand anything on this simply giving you guys this slide so you can answer some of these questions, because oftentimes, like you've seen some of the things from like the Fallout games and stuff in here, there's all sorts of things that, and people can use different units to express essentially the same thing. I want you guys to realize that these are all units that have been used from time to time throughout history. Like sieverts are pretty much our standard unit, but that's our absorbed dose unit. So it's not necessarily just like the beeps on the Geiger counter. So in order to go from the beeps on the Geiger counter, you essentially have to multiply it by 1, it's somewhere between 1 and 20 to get like an actual dosage. Does that make sense? Depending on what type of radiation it was. And I had that Geiger counter out in class and it was just beeping. Chances are almost none of that is alpha particles. Because alpha particles get stopped by literally everything. So chances are if it's beeping, it's probably going to be something like the gamma ray, the X-ray, or the electron that are causing disaster. Does that make sense?
Yeah,
Yeah, I showed it to you all that. Okay, well, that's it for the notes. So we're essentially done on that, so let me stop recording.